Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, fantastic turnout. Thanks a lot for coming to this first research parallel session. I'd like to introduce John Wynn, who's the principal researcher in the machine learning group. Actually, John just told me he was the #1 PhD scholar of our then not official PhD program, started in 1999, so 5 years before the official launch of our PhD program, when everything was really informal and money. Well, there was budget available. You would fund the students. So John is one of those. The #1.
They were just brown paper bags of money.
And of course, ever since then, I have had quite a few years career in Microsoft. Now principal researcher, and he will tell us a little bit about his research in machine learning. Thanks, John.
Thanks, Scarlett. Okay, so I'd like this to be an interactive session. There's quite a few of you. But if you have questions, if there's anything you want to ask, then please do so. If it gets super hot, and you need a water break, then run out and get one. Okay, so what I want to talk about today is probabilistic programming. This is something that I've been working on since 1999, in fact, even before that. Although perhaps I didn't realize it at the time. I think it's a really exciting sort of new way of thinking about machine learning and a new way of thinking about programming. So if you're interested in either of those things, you're in the right place. So what are we going to look at in this hour? So for those of you who don't know what it is, we're going to explain what is probabilistic programming and why it's important if you have a machine learning task you want to solve. And I'm going to dive in on a couple of real examples for using it to interpret user behavior, using it to parse unstructured text. And the last section is really going to be more technical on some challenges on getting probabilistic programs to run sufficiently fast. Okay, so let's get started. So here we have some code. I'm afraid there's going to be quite a lot of code in this talk. So what we do is we have this nice piece of source code. We're going to create some strings, format them together, and then print them out to the console. So hopefully this is clear enough to most people, except that unfortunately our lawyers have been on the case, and they've redacted some of this source code. So I can't actually tell you what's in these two black areas here. Happily, you can buy our compiled code and run it yourself. And when you do that, what you'll find is that it prints out hello uncertain world. So, you're all smart people, you can see the source code. What were the strings under the black boxes? Anyone feel brave this afternoon? What's under A?
There are possibilities.
Two possibilities.
Hello, uncertain.
Yes, absolutely. And if you have no reason to favor one string over another, then you might say there's 50% probability of hello and a 50% probability of hello uncertain. And similarly, for B, world and uncertain world, so full marks.
But can't it be that B is empty string and the other one?
Ah!
There is a space.
The space is the constraining factor here. So there's only two spaces in this string, so this space has to be one or the other. That's the two. I'll leave you to work this one out for yourself. Okay, so this sounds like a fun thing to be able to do. We'll put sort of black boxes in our programs. And this is the sort of essence of probabilistic programming. So let me write this problem again as a probabilistic program. So what I'm going to do is I'm going to write in a language called probabilistic C#. So C# is obviously a Microsoft language. Who codes in C#? A few people. It's very like Java. But probabilistic C#, and we sometimes call it C soft, as a sort of little joke, is just like C#, except it has a few extra bits. And one of them is this thing called random. What random does is it takes a distribution, I'll be talking more about this later, but it can return uncertain values. So what this says is the result of this is some unknown string, equally likely to be any string. And so from this point in the program, A has that value. It doesn't have the value hello or, my favorite string. It's equally likely to be any string. And the same for B. And then we can work with these uncertain values just like we work with normal values. So we can format them together, we can write if statements, we can write loops, we can do all the sorts of things you do in normal programs, but now we're doing it with uncertain values. Make sense? Yeah.
Uniform distributor can only be defined on a constraint domain, but the domain of strings are unconstrained.
That's a very excellent, good point, well observed. So the set of strings is infinite, and this is an improper distribution over that infinite set. You may want to consider, if it makes you feel more comfortable, the fact that the set of strings is not, in fact, infinite, because the memory size of your computer is finite. And most programming languages will actually put some practical length on length of the string, but it is actually quite convenient to be able to work with improper distributions when you're working with strings. Okay, so that's an improper uniform distribution over strings, and then that's an unknown string. Now we need to be able to have the equivalent of running the program and observing the result. So we have another operator called observe, which says that I ran this program and this was the result. Okay? Not assignment, it's a constraint that says, once I did all this, this was the output. All right? So in this case, we're saying once I picked A and picked B, or I had my unknown A and my unknown B, and I did this, and the result was this. Make sense? And then the final piece of the puzzle is that if that's true, it's actually... Yep.
So it's not possible because C needs to have like double
exclamations.
Spotted a bug in my slide. Okay. Mentally insert the exclamation marks, if you will. I actually added the exclamation marks to give it more punch, and I didn't do it in the right way. So we only need to be able to get back the new uncertainty once we've taken into account these additional observations. And so we have this construction called, this function called infer, which given a variable which has an uncertain value, returns you a distribution that captures that uncertainty. So in this case, it's going to be some distribution that captures the fact that we're 50% hello uncertain and 50% hello. And similarly in this case. So this is probabilistic programming. It's a very powerful form of programming, and almost all kinds of machine learning, in fact all that I'm aware of, can be expressed as a probabilistic program. And we'll see lots of examples of that. So let me just dive into then more precisely what we're adding to C# to make it probabilistic. So as you've seen, we have random variables. So all the variables you'll ever have worked with in your programs have a fixed single value. An integer had length of 6, or a Boolean variable was true. And what we're adding now is the ability to go beyond fixed single values to uncertain values. So an integer may be uniform between 0 and 10, or a Boolean may be visible with probability of 80%. So it just means is distributed as. Yes?
This random class, is it the same as the default random in C#?
No, it's very, very different. Well, I'll come back to you on that one. Good question. So we have observations, and these are just Boolean statements that just say, this is true at this point in the program. And so that then has to propagate backwards up the program in order to influence the things that have already happened. And then finally, our infer statement says, given all of our distributions and all of our observations, what is my uncertainty in this variable now? So here's another example. I want you to sort of make sure you get this one. So here we have an integer, and it's uncertain value between 1 and 10, uniformly on each value. Okay? And now I'm going to say that we have another variable, which is that number squared, is that greater than 50? So it's true if it's greater than 50, false otherwise. So this is now a random variable as well, right? Because its distribution is equally uncertain. And so if we inferred back this distribution, we would get, well, the answer's on the slide. But if anyone wants to shout it out, yeah, 30% of the time, this is going to be true, and 70% of the time, it's going to be false. Yeah.
So I guess one thing that I don't really get, or let's say what confuses me is that, so is that a distribution,
No.
or is it a value that gets set at that point based on the distribution that you define on the right-hand side?
I is just a variable, like an ordinary variable in a program. What is a variable? It's a named quantity, right?
So whenever you call that, then you would pick something out of the distribution, out of the uniform distribution.
No. It is just an uncertain quantity, right? This is a new way of thinking. This does not have I does not have a fixed value. It has an uncertain value, and we're doing computation with that uncertain value. Okay.
There should be another operator, not equal, but maybe like distributed as, like tilde.
Yes. So bugs has a distributed as. We just use random. So it means take this distribution, which represents some uncertainty, and turn it into an uncertain value, and then assign it to R. Yeah.
Is it correct to think of these as having a sampling semantics?
I'll come to the sampling semantics in a few slides, but yes, you're absolutely right. So I really want to push on the fact that these are uncertain values, because one of the sort of disconnects, in my opinion, between computers and people is that people are continually happy to deal with uncertainty and to express uncertainty, whereas computers always require precise values. And often when we're interacting with them, that's a point of disconnect. And so it's actually much more natural when you're programming to be able to program with uncertainty, right? How many times have you written a program and thought, I have to put a number in here, I don't know what that number is, so I'll make one up. Well, wouldn't it be better just to actually say that I don't know what that number is? Okay. So one thing to note is that even if B is random, the output is a distribution that captures the uncertainty, and B is not random. So you can think of this as gating the randomness in your program. All right, so let's look at a standard machine learning. Is that a question? No. Okay. Let's look at a standard sort of statistical machine learning problem expressed as a probabilistic program. So everyone familiar with linear regression? No one's going to admit that they're not. So that's good. So, so linear regression is you have two variables, x and y, and what we want to do is we want to predict y from x and assume there's a linear relationship between the two. A linear relationship has two parameters, a and b, the slope and the intercept. So we don't know what those parameters are, so we're just going to pick them from some really broad distribution. Okay? So that's just like a can be anything between, plus and minus 2 or 3,000. Same for b, these are just really broad Gaussian distributions. And I'm going to iterate across some points. So I'm assuming that I've got an array of x's and an array of y's that someone has given me. So some scientist has done some experiment and said, here's my x's and here's my y's. And what I need to do, first of all, is make here's the equation of a line. So my x multiplied by a plus b is a clean version of y. Now, this is not going to match perfectly the y that I've been given from this experiment, because lines never go exactly through data points. So we need to add some noise to simulate that process. So we're going to add some noise with unit variance, and then observe that that is equal to y. Okay? So this is linear regression, Bayesian linear regression, in 1, 2, 3, 4, 5 lines of code. And then we can infer back a and b, and we fit the line to the point. So it's just a very, very, very powerful way of doing analysis, of doing machine learning, very compactly. Question?
How do you set the variance of the noise to 1?
I just did, so that it would fit on one slide. If you didn't want it to be 1, supposing you didn't know, right? Then you can make it another variable and draw that variable from some part. Yep.
maybe I didn't understood something, but the inner loop has no effect on A and B. Basically, the inferred value of A is Gaussian.
No, so you've got the observations, right? Observations are a very unusual thing if you're used to thinking about programs, because they have effects that propagate backwards up the program. This observation tells you something about the clean Y, which in turn tells you something about A and B. Okay? I'll give you an interpretation of this shortly that will make more sense. Yeah.
Please correct me if I got this wrong, but I see observe as emitting something, and then infer runs expectation maximization on what is emitted.
That's not quite right. So I'll skip straight to in fact, I think it's the next slide. Sampling interpretation. Okay, so you're confused about what these programs will do. All right? So let's work out a semantics that will tell you what they will do. This is not how we run the program, this is how we define the semantics of the program. So what you do is you run the program an infinite number of times. Okay, that's important. So you run it a very large number of times, but in some cases it has to be infinite. Random now does sample from the distribution. Now it just samples from the distribution. Observe will just throw away the run. So if the constraint is false. Okay, so if you hit an observe and it doesn't apply, then you just throw away everything that you've done and start again. And infer x stores the value of x in some memory, and then when enough x's has been stored to characterize a distribution over values, outputs that distribution. So it might be an infinite number. Okay, so let's apply. Well, lots of questions. Okay, yes.
But we know that for some cases you have to sample really many times, sometimes to get the correct
yes, that's why we're doing this infinitely many times. Okay? So in your program, run this infinitely many times and you'll get the right answer. It's not very efficient, but it works. Actually, I can't say it works. I guess it's never actually happened. Go ahead.
So in this way, you can only get a numerical distribution from infer x. Can you get a functional form from infer x?
Well, you can then fit a function to those samples. And of course, if you've got infinite samples, you can do that infinitely precisely. Yep, the back.
In the previous example, you showed that so function can show that there was B should be a Gaussian. How it will work in this case?
I'm sorry, I didn't catch that.
In the previous example, you showed that B should be a Gaussian. So it should take Gaussian distribution. How it will work in this case? We can discard it because.
So are we talking about this model again?
Yeah.
So let's go through that process for this model. Okay? All right? So we pick some A and B, right? So then let's suppose we picked by magic the actual, we pick some A and B, and then we compute a clean Y, and then we add noise to that. And with zero probability, with very vanishingly small probability, we'll actually hit the actual data. Okay? That's why we have to run this an infinite number of times. For the ones where we do, pick A's and B's that fitted the data well, because they were close enough that we were likely to get some noise. And so if you actually run this, you'll get back a distribution over A and B, which are not point values around the line, because there's uncertainty in what that line was, but which capture that uncertainty appropriately. I'm going to have to move on, because otherwise I will run out of time. But get me afterwards if you have more questions. Okay, so we don't actually run probabilistic programs by running them an infinite number of times, or even a very large number of times. There's two general approaches to running probabilistic programs. You can sort of interpret them line by line, or you can compile them to generate sort of machine learning algorithms to compute the outputs that they would give. And in this building, or in this lab, we've been working on a compiler called infer.net, which can take a probabilistic program and solve it for you for a wide range of probabilistic programs, by far from all probabilistic programs, but a wide range, a useful range. And it scales, and we've used it a lot. And you can get it here. So I won't talk much about how it works, but it gives you that language, it gives you that expressivity that you can sort of express your program and then just say, give me the distribution for these variables in the program. Okay, so why is it important? Let me talk about something that actually happened. So this is a ways back now, 2005, 2006. Xbox Live came to us and said, we've got a problem. We've got this game which is quite popular called Halo. You've heard of it. And at that time, well, this is actually 2007, they were having all these millions of people playing, millions of matches. And what they wanted to do was give people a great experience playing the game. And what the problem was that they had to match players coming online with other players online of similar skill. Because if you play someone who's much better than you or much worse than you, then you have a terrible time. And in order to do that, they had to work out how good people were. And they had to work out how good 12 million people were continually every hour of every day. And so some researchers in the lab worked on this for about 6 months, wrote an algorithm which was sort of hundreds of lines of code. And what it would do is it would take some Gaussian distributions that estimated the player's skills, and then it would take a particular game and it would create some new estimates of the skills. So this is obviously quite a lot of work and took quite a lot of time. Let me show you an example of what it might do. So here's a game. Here are the skill estimates before the game was played. So we have 3 players. Sully, who's a new player. We don't know much about their skill at all. So we have a big, wide distribution. Then we have Sniper Eye, who's an experienced player, played a lot, and we're very confident that his skill is close to 30. And then we have Dr. Slowplay, who is sort of somewhere in between. He's not played as much as Sniper Eye, and he's not as good. Now this game happens, and what happens in this game is that Sully comes first, Sniper Eye comes second, and Dr. Slowplay comes third. So what might you expect to happen to these curves given that outcome? What might happen to Sully? Yeah, shift to the right and get sharper, right? So here's what happens. And here's what happens to Sniper Eye. He goes down very slightly because we're already pretty confident in his skill. And here's what happens to Dr. Slowplay. He also goes down a bit more. So the computations to do that, as I say, 6 months of work with a researcher and lots of effort. Or this much code in probabilistic programming. So this is a probabilistic program for that system, which is called TrueSkill. And so what we do is we assume that we've been given the means and variances of the skills to start with. And then we have a number of players. And the assumption in it is that everyone has a skill, and when you play a game, you have a certain performance. You may play better than you normally do, you may play worse than you normally do. So your skill is like your average performance. And so whoever wins the game will be the person with the highest performance. Make sense? So in order to simulate a game, what we do is we say the skill of the player is an uncertain variable with this mean and this variance, which we took from our database. And then we're going to add some noise, which is like how much your performance can vary from the typical, and add that onto the skill. So it's performance is skill plus noise. Then our observations come in, and this is where it constrains the skills. So for all players after the first one, we observe that the performance of the previous player was higher than my performance. The players are ranked in order. Okay? And infer skill gives you the new skills. Pretty powerful stuff for that much code. And this has been running on Xbox Live, not using probabilistic programming, since 2005, 6-ish.
How much time does it take to run this for 12 million players?
I think InfiniNet, last time we measured it, does about 8,000 skill updates a second, something like that. It's getting to the point where the data loading time dominates. Okay, so that was one motivation as to why probabilistic programming is important. It lets us solve these big problems in small amounts of code. But I would argue that machine learning is becoming much more common. Right? We hear about big data all the time. I hate the phrase, but there is a lot more data around these days. Everyone wants to get their useful information out of their big data sets. And increasingly, we're also asking more complex questions of that data. We want to build more complex systems, speech-to-speech translation, self-drive car, personal assistants. These are not simple systems. They're highly complex systems. And they're larger scale than ever before. Okay, this is another interactive bit. Okay, so you're all working on projects. So I want you to stand up if your project involves data. Okay, that's all the theorists. All right. I want you to remain standing if you want to do some sort of analysis or machine learning on that data. Well, that was, okay. I want you to remain standing if your data is bigger than 10 megabytes. 100 megabytes. A gigabyte. 100 gigabytes. Very impressive stuff, guys. Okay, thank you very much. So the point is, you're all trying to solve well, not all. Like 90% of you are trying to solve machine learning problems, and a significant number of you are doing it at large scale. I don't have a way of asking you how complex your problems are, but I'm assuming they're more complex than the previous generation of problems, otherwise you wouldn't be getting PhDs out of it. So all of these things, therefore, are true, demonstrated in this room. So how can probabilistic programming help with these three questions, with addressing or helping with these three aspects of machine learning? Okay, so my argument is probabilistic programming requires less expertise, possibly much less expertise. It certainly does still require expertise, but you don't need to know about all the algorithms that run to provide the answer. You just need to know how to pose the question, which is still a task in itself. And increasingly, one of the challenges we face is to make it easier and easier to use these programming languages. If you think about programming back in the 60s or 50s, it was done by maths PhDs. And that's ordinary programming. And if you were to ask one of those PhDs back in those days, can programming these computers become a job that anyone could do, they would say, no, you need to have a maths PhD, right? And the reason why that's no longer true is because languages have gotten easier to use, tools have gotten better, all the support has gotten better, documentation, books, training, the whole ecosystem is there, helping people to do it. We are still, with machine learning, at the stage where you kind of need a PhD to do it. And it would be great to move away from that. I mean, I don't want to put us out of a job, but there'll be more PhDs. By being shorter and being written in a standard way, probabilistic programs are transparent. You can look at one. Someone can give you one and say, here's my program. You can go, oh, yes, I can see what assumptions you're making about the data. I can see what you're doing. Rather than handing you like 2,000 lines of algorithm, they hand you 20 lines of program. And because they're short, you can play with them. As you know, I'm sure, the faster the cycle of experiment results, the faster you learn, the better results you get. So because they're short, you can say, oh, I'll just try this thing. I'll just do that thing. Our goal with infer.net was to get it so that we could go from the whiteboard description of what we wanted to do to actually getting it working in a day, when it used to take 3 months. And we do that nowadays. Complexity. To some extent, programming hides the complexity. The program might be quite complex, but the inference algorithm that runs behind the scenes is usually an order of magnitude more complex. So some of it is hidden away. And also, as we start to look at programming languages are sort of experts at hiding complexity. We have libraries that hide complexity. Someone else built it and knew about that domain. So again, all of the tricks that software developers and programming communities have developed over 30, 40 years, 50 years, we can steal and use for machine learning. The actual inference engines are doing hairy maths. Even the best people in the world make mistakes when they write these algorithms. If they're reusable, tested multiple times, they're more likely to be right, and therefore you can build more complex things. And as I said, we need to use tools and support infrastructure to make managing complexity better. And finally, for large scale, probabilistic programs say what the problem is, not how to solve it. So take that linear regression. It says do a linear regression. If I had 1 billion points to do a linear regression on, I could imagine in executing that program that I would execute it not on one machine, but on 1,000 machines. Okay, it'd be a pretty dumb thing to do because it's a linear regression, but you get the point, right? You can execute it in any way that you like. And in doing that, I'll skip over these really, but you can do it in a parallel way, you can do it in an online way very easily. All right, let's go to a couple of examples.
Quick question.
Yes.
Is there any danger of writing this program that potentially ignoring completely how inference works?
Absolutely, but that's true of ordinary programs as well, right? When you're writing an ordinary program, you have to be aware of how it's going to execute to some extent, right? But only when there's problems. Anyway, if it doesn't run fast enough, or you run out of memory, or whatever it is. And it's the same here. As much as possible, we'd like to make it so it just runs. We're far from that right now. Even for, well, we can do that for some cases, but that was also true of traditional programming as well at one point. So yes, having more understanding of how the underlying machine learning algorithms work is useful. But you don't absolutely have to have it, and you don't have to have it in as much depth. Yeah.
In terms of debugging and testing this, what
Yes.
kind of stuff would you expose for curiosity on underlying algorithms and invasion methods?
So we have some things. This is still very early days for this. There are essentially no tools. I'm very keen on building a debugger. If anyone wants to come and help me build a debugger, that would be great. The idea that you can put a breakpoint on a message passing algorithm on an edge of a graph and say, break when this message gets passed and show me the message, that sort of thing. We don't have any of that. Well, we have some of that. But yeah, the big void where tools should sit right now. Yeah.
When I write traditional programs, I have some notion of the complexity, like the big O notation. But do I have a similar notion of complexity when I write probabilistic programs?
That's not a question I can answer quickly. It will depend on what algorithm you're using to execute the program. We've looked with info.net at things like, if you tell us the program and the algorithm, we will tell you the big O notation of it. But getting that sort of more like as you're writing it, again, unexplored ground. Yep.
So how does it handle like varying number of variables to it?
It just does. The paradigm supports it.
Yeah, I know, but for example, you can imagine something like Camille's clustering, and you also want to estimate the number of clusters.
Yes.
And maybe these clusters have also some properties.
Yes.
So then the distribution becomes really complex, right?
Yes.
And it's complex and not like
the structure can be uncertain as well as the quantities. Yes. Yeah. So you can define all these problems with probabilistic programming. I'm not saying we can solve them yet. There are programs out there that do sampling that can certainly solve that kind of thing because they're only providing samples. I love these questions. These are great questions. I can chop off the last chunk of the talk and take more questions, so I'll do that. Okay, go.
You mentioned the possibility of using GPUs for influencing probabilistic programs, right?
Yes.
Has anyone done any research on that already?
No. So there's I think that the church guys did something very cool. They did FPGAs for executing probabilistic programming. And there has been some work in Microsoft on using FPGAs for executing machine learning, but not for a probabilistic program. Field programmable gate array. It's like hardware that you can configure on the fly to do particular things rather than a CPU. It's generally faster.
Also does it on GPU, like supports GPU? Was that a question?
Yes.
Yeah, so Piano also does
Okay,
that.
thank you. Yeah, so I'm not totally up to date on who supports GPUs and who doesn't. As yet, we haven't done much on GPUs. Yep.
Could you give some insights into opportunities that infer.net can discover for parallelization of a probabilistic program?
That's another great question. Okay, it's all good questions. Yes, so parallelization, I sort of skipped over it on the previous slide, but if you know the program, that tells you the full structure of your model, if you're thinking of a graphical model, which tells you all the independence assumptions. And so actually what we get in the middle of infer.net is what we call a logical inference algorithm. It's an inference algorithm, so the algorithm that you'll execute to compute your inference results. But it's expressed in a logical way, in the sense of, we need to do this computation from this data, and then pass this data to this other thing, and then do this computation, and so forth. And it's exactly, it has parallel structure already. So if you want to execute that on parallel hardware, you can. We actually do work to schedule that on a single CPU right now. So currently, we have a parallel algorithm that we then schedule back onto a single CPU. Okay, so let me give...
Is it possible to learn the distribution of a set of data points? Like if someone just has, I don't know, 1 million data points, to maybe 1 million points is too much, but 1,000 points, is the program able to say these are, I don't know, generated with a Gaussian distribution or something like that?
Can I answer that after the talk, because it's quite a long answer? I do want to get a couple of examples done. I'm really running out of time. Okay, let's go to some real examples. So, this is Bing. It's like Microsoft's Google. And so when people type in a query, they get some results. And rather handily, what will happen is they will click on those results. They might click on the result. And we can track that. So we get a click log where we get a little true happening when they click on the result. And maybe they didn't then come back and click on the second one, but perhaps they then came back to the search results and clicked on the third result. And we can track that. And these clicks are gold, right? They tell us everything that our ranking algorithms couldn't do. So it's because it's people. And so we'd love to be able to use them to improve our search engine. And so the naive thing you might think is, well, if you click on something, then we should boost it, right? But there's a couple of problems with that. You might think of them yourself. One of the problems is you're more likely to click at things at the top than at the bottom. So even if there's a great result at the bottom, you might not click on it. Another problem is that you're judging whether to click on the basis of these little snippets here. And if you have a snippet that's incorrectly alluring, you may go to that website and then be disappointed. Or if you have a snippet that's incorrectly disappointing, you may skip a result that actually would have had what you wanted. All right? So if you just count clicks, then you can make these various kinds of mistakes. So how can we correct for both of those effects? Well, we could use a probabilistic program. Now, here's the thing about probabilistic programs. In ordinary programs, you're programming a computer to do something, right? You give it a program, it does something. In probabilistic programs, you're building a simulator of the world, okay? Because what you're going to do is you're going to attach data from the world at the end, and you're going to infer back all the things that happen. So in ordinary programming, you're programming a computer. In probabilistic programming, you're programming the world. Right? So here we're programming a user. We're writing a little program which defines how a user behaves when they see some search results. Okay? So here's a user. And he's going to look at some search results. So he just typed in a query, he's going to look at some search results. And he's going to examine the first result. And he's going to decide, based on the snippet that he sees, if he's going to click. So we have, we assume that each snippet has some appeal, which is a random variable. So it's going to be the number between 0 and 1, which is your probability of you clicking on that snippet for a given query. And so we're going to create the click random variable using the appeal random variable in this way. And the Bernoulli distribution is true with the probability given in the brackets. Okay? So if appeal is 1, you'll always click, and if it's 0, you'll never click, and somewhere in between. You'll click that proportion of the time. Then he's going to go and look at the website, and now he'll find out if it really was relevant to his query or not. Okay? So again, while snippets had appeals, web pages have relevance, which is the probability that you will find it relevant to your query. Now let's suppose he's unhappy. He didn't find a relevant page, despite the fact that the snippet looked good. What's he going to do? Well, there's two possibilities. He may give up, or he may continue. So here I've just hard-coded the probability that it's 90% likely to continue. So he goes to the next. The assumption is, in this model, he goes to the next result down the set of 10 blue links and looks at that one. And again, he'll decide if this snippet appeals to him. And he'll look at the web page, and it will have some relevance. And then this time it's relevant. Even if you find a relevant result, you may still choose to go back to the website to look for some more results. But perhaps that's much less likely. Perhaps it's only 20% likely to happen. And so, if not, we're done. So that whole process, a little simulation of a user, can be written in very little code. This isn't the whole code, but this is the important. So we have, here we have our unknown appeal and relevance for each document. And a beta distribution is a sensible distribution to use because it gives a number between 0 and 1. And then this code below, for each user and document, just says if I looked at the previous document, then I have a chance of looking at this one, only if I didn't click on the previous one, and this variable, which is true if I'll go on if I didn't click, and if I did click on another variable, will I go on if I did click? And then so on for whether I'll click if I examined it, and whether it's relevant if I click it. Okay, then to attach the data, we actually have this log for now for many users. I can just iterate over the users and just observe the data onto the program. All right, so let's see it in action. So here it is. This is actually running. So what I have here is a simulated data set. I can control how many people did each of 4 things. Clicked on both of the first ones, just the first, and didn't click on the second, skipped the first and clicked on the second, didn't click on either of them. And I'm just looking at 2 links for now. And what we can see, let's suppose, for example, that all users, in fact, clicked on both. What does that intuitively tell you? They click on the first link, and they come back and click on the second link. Exactly. So, but that it was appealing enough to click on. Right, so what you see, what's happened is the appeal has gone, this first link has gone to almost 1, and the relevance has gone to almost 0. So we've learned, despite the fact they clicked on it all the time, that it's not actually a relevant document. If a few more people had not come back, then its relevance would sneak upwards. Okay? If, on the other hand, more people had skipped over this first document, then its appeal would have gone down. And if more people skip over both of them, its appeal goes down further. So that's already quite a complex relationship, even for just 2 links. You have 10 links, it gets even more complicated. And yet using this program, we can compute these quantities. And we can understand what assumptions it's making about the user behavior. You may not agree with them. The user might go 1, 2, and then skip to 6, right? Fine, change the program to represent that. But at least you know what assumptions are being made when you analyze the data. Okay, one more. So, I'll finish at the end of this section. So strings are fun with probabilistic programs because they're so sort of much more informative than numbers. So this is an example where we have a string, which is any capitalized string. So that's any capital letter followed by some lowercase letters. And we're going to format it into another string. This is string format, so we'll just substitute this string in where we have this placeholder here. And then we're going to observe, that this result, equals my name is John. All right? So if you do this and infer name, you'll get back a distribution which is 100% John. Excellent. Right, this is fairly boring. You can do this with regular expressions or even simpler things. So let's do something more exciting. Let's learn the template. So this thing here I call the template, the thing with a placeholder in it. So let's learn that. Let's make that a random variable as well. So now I need something a bit more complex as the prior for the template. It's going to have a placeholder in it. So we'll have any string, and then some non-word character like a space, then my placeholder, and then some other non-word character, and then any string. And actually, the any strings can't include placeholders. So now I'm going to insert that as my template. And now, rather than inferring the name, I can infer the template. And so I'll get my name is placeholder. Okay. So I think you can perhaps see where this is going. What happens then, if I change this string from my name is John to hello, my name is John. I clicked ahead. Who was observant? So what's the distribution over template in this case? Who's still awake?
The old one or the one mine?
You saw it. Well, you saw it. I'm sorry. So it's either hello, my name is blank, or hello, blank, name is John. Because both my and John are capitalized. Okay? This is a very dumb program. It doesn't know about names, right? It just knows about putting strings together. So how can we solve this problem? How can we learn the right template? Well, I could build a fancier program. I could build in some knowledge about names. I could take census data and say, these words are likely to be names. Or I could just throw more data at the problem. Let's throw some more data at the problem. There's not actually a shortage of text. So we can do that. So here we just take a second name and a second piece of text. But a common template. So the template variable is now shared between the two. And another piece of text, hello, my name is Andy. Okay? And now, if we infer back the template, there's no ambiguity. So not only is the name is now John and Andy, and the template is hello, my name is blank. And this is actually a really useful thing, because if you are trying to learn, say, to extract information from the internet, then there's lots and lots of text. It's quite easy to find text which is the same text with values changing, and it's very easy to learn templates in this way. You might want to go one stage further and say, well, what if the things that I want to work with are not strings? What if they're dates? Then I want to be able to deal with uncertain dates and uncertain strings. So I need to be able to convert between the two. So this is any date. I'm going to have to format it into a string. And I'm familiar with how to do that. I have date format commands in my language. So I can pick a format. So I'm just going to pick one of these formats. And then it's going to format it to a string. And now I need a template with two placeholders in it. Now if I give it the text, Fred was born on 6th of May 1963, and I run the program, then I can pull out the template. 0 was born on 1, the date string, 6th of May 1963, the format, the date, and the name, all in a handful of lines of code. So you can start to see the power of this system. Build up complex models of generating text, attach some real-world text, and invert it. So let's look at a final example. So who's working on biological applications? Anyone? A few people. Great. So you might be familiar with this. This is a sequence motif. And the idea is that in DNA, for example, you find subsequences that have particular biological meaning, perhaps. But they're not fixed sequences, they're probabilistic sequences. So certain elements of the sequence may be very likely to be certain bases, and other ones might be one or the other, and other them might be very uncertain indeed. And so here are some example sequences that match onto this sequence motif. Well, here's another interactive part of the talk. I'm going to show you some data, and I want you to spot the motif that is present in this data. Put your hand up when you see it. Anyone? Yeah, it's a joke. You can't actually do this. But here's a program that can, and it fits on a slide. So there's software you can download to do that task. And here's a slide that does motif finding. Probably not as well, but so what are we going to do? We're going to say we have a motif. We don't know what it is. But it's going to have a probability at each character of each value, drawn from some suitable prior, here a Dirichlet distribution. Then we have this set of sequences that you saw on the slide. And so we're going to generate from that probabilistic motif a particular motif instance that's going to appear in each sequence. And we do that by drawing an integer from that probability distribution and then casting it to a character. And then we're going to choose where in that sequence the motif sits. And then we need to generate some background sequence either side of the motif, which we're going to draw from some background distribution that we've been given. That's left and right background. And finally observe the result. So, take this program, take the data I just saw, run the program, and this is what you get. Pulls out, and in fact this was synthetic data, so I knew what the ground truth was in this case, and it pulls out all of these sequences. It makes one mistake, up there on the top right, although this is the most probable position that is shown, and the ground truth does have a quite high probability. And then it learns this motif, which is essentially extremely close to the ground truth motif. So very powerful stuff. Okay, I'm not going to do this last section because I ran out of time. I will skip to the end. Okay, so probabilistic programs can solve complex problems. You've seen that. They can be very quick to write. Hopefully you've seen that too. And they can be fast to execute. They can also be very slow to execute. So this is a really huge area for research. So where do we need more work? This is a new area. Speed. Fundamental thing. It's very easy to write probabilistic programs. It's very hard to make them run fast. In addition, speed. It really is. If we have lots of exciting programs that we would love to run, but we cannot. So apart from that, there's also ease of use, reliability, debugging, training, examples, books, build up of experienced people and all this kind of stuff. But I think we're at year 1 or year 3 or 4 of 100 years of probabilistic programming, and it's a very exciting time. So I'd really encourage you to either learn about it, get involved, or use it for your applications. And my hope is that in the future, every programmer will be writing probabilistic programs and therefore doing machine learning. Thanks very much.
Questions. John also offered to hang around on the tea break a little bit and follow up with some questions. So.
Okay. Maybe my question is a bit stupid, but actually I don't see why we need a new programming language. Because cannot we wrap all these probabilistic things into something like monad and run it on the top of some existing programming language? This will give us existing, reusable infrastructure such as debuggers, profilers, and so on.
That's a great question. I'm all for that. Probabilistic C# is C# with just these three things added. The thing is that because you're executing it in a different way, the standard tools, the standard profilers, perhaps the standard debuggers you can use them, but they aren't well suited. They don't map really nicely because they're running on the sort of the generated algorithm rather than the original program. So there's but the more you can use an existing language, the more you can take advantage of people's knowledge, of experience, of all the wealth of tutorials and libraries out there and all that kind of thing. But that said, making a library that's, say, written for C# run as a probabilistic library is a whole other ballgame. I'm not aware of any language that can really do that because they're generally written in too complex a way. But that's something we'd like to be able to do. And in fact, Ali here is working on a way in which we may be able to do that. And that's the part of the talk I skipped, I'm afraid, which is how we might be able to get library-like code where we can't actually get into it to run efficiently inside a probabilistic program.
Yes.
It seems that there's a high effort for someone creating one of these programs to figure out what kind of model to create, and we can imagine that there are many things you could tweak. Okay, do I model the click with this variable, or do I model it with that one? Does infer.net have capabilities to compare models using, say, cross-validation or some complexity penalty or something like that?
Yes, it's called if. So if. Yes. So in a probabilistic program, if you have two programs that you want to know which one is better at explaining your data, then you just say if some random variable, like program A is better, give it a 50-50 distribution, and say if A, then A generated the data, else B generated the data, and then infer the posterior distribution. And so you can compare models within the infrastructure of probabilistic programming itself.
Still need a complexity penalty,
No,
right?
the complexity penalty is built into that. I assure you.
Can you have some guarantee or on the results you get of the algorithms behind the... Because you might compare two models, but if they are solved by different algorithms, you don't know what happens.
So I've talked about probabilistic programming. I haven't talked about how we execute them. And generally, we'll use approximate methods. And the approximate methods may be differently accurate for two different models. So it might be that you give the approximate estimate of the evidence for one model may be worse than the other.
Not know if you compare two models, then you may not know if one is better because you have solved the model better, or because just it's a better model.
Sorry, you may not know if you...
So if you compare two models,
yes,
but they are not solved using the same algorithm.
Well, you can always choose to solve.
But if you have no guarantee of the approximation,
Yeah.
how can you compare them?
Yeah, that is an open question, right? I mean, most of machine learning that happens is using approximate inference algorithms, right? 99%.
Yeah, I know.
So very few of those algorithms come with any guarantees.
Okay, we'll take one more question, and then the others, the lady in the...
So about these algorithms, is this information available somewhere? How exactly, which algorithms you use?
To execute the program?
Yeah.
Yeah, so Infinite Network comes with a few algorithms, general purpose algorithms built in that you can choose between. There's expectation propagation, which is a generalization of belief propagation. You may also know it as some product. There's variational Bayes, variational message passing. You may also know it as EM. And then there's sampling, Gibbs sampling, block Gibbs. There's three options you have. It will actually generate some code. So you can actually see the code. You can do the exact algorithm that's running. You can then tweak it in various ways. So you have a fine degree of control over the way in which inference actually executes, or at least you have a fine degree of ability. You can really inspect what it's doing. You have less control actually than that, but you can inspect what it's doing to quite a degree. You can step through it in a debugger, for example.
Other question?
How is this different from quantum computation?
We actually have a workshop on that next year where we're bringing probabilistic programmers and quantum programmers together because they think, or both communities think we can learn from the other. So I'm no expert on quantum computing, but it does seem to have some of the same primitives, right? It has this uncertain Boolean, essentially this qubit. And you can bind them together and then collapse those uncertainties of the variables and essentially take a sample at the end, which is very similar to inference. So I'm very excited about the potential for quantum computing for doing machine learning. That's about as far as my understanding goes. So I think it would be a really exciting area to explore.
Okay, thank you very much, John.
Thanks.